Okay, in this example, we're going to look at Pascal's principle and how a confined incompressible fluid, right here, is going to give us a mechanical advantage. So this is our apparatus that we're looking at. We have, as I said, confined fluid. We know the surface area of the small input piston, A1. Okay, so we're told that A1, that's the small area, has 3 square meters. Okay. And the big output area is 113 square meters. So this whole apparatus is on a very large scale. Okay, 113 square meters. All right. And we want to use this to lift a car. The car has a mass of 1,100 or 1,100 kilograms, and it's resting on the large platform, right? So the car is over here. Okay. So this is the location of the car. All right. All right, and the car, so the mass of the car is 1,100. Okay, that means that its weight of the car is going to be 1,100 times 9.8. So let's go ahead, 1,100 times 9.8 to 3 sig figs gives us 108. So 1.08 times 10 to the 4 newtons. Okay, so that's our F2. Okay, so we're going to use Pascal's principle. Okay, and what is Pascal's principle? Well, it tells us that A1, well, actually, really, originally, let's start there. It tells us that P1 has to equal P2. So in other words, pressure is conserved. The pressure at any point has to equal the pressure at any other point. Well, that means that because, besides the pistons, the rest of this system is unmovable. It's all rigid walls. But the pistons are free to move, so that's the parts we care about. So then we would have pressure 1, which is force per area. We would have F1 divided by A1. And that's going to equal the pressure at point 2, which is F2 divided by A2. Okay? And we're asked for how much force it would take to lift the car. Okay? So in other words, we know F2. All right? So we have that F2 is just going to be the weight of the car. All right? So that's the 1.08 times 10 to the 4 newtons. Okay? So then we need to solve for F1. Okay, so then F1 is going to equal, all right, so cross multiply A1 both sides, so I end up with A1 over A2 multiplied by F2. All right, so that's going to give me that F1 is actually here. Let's just put it on this line over here, but we'll put the values in the calculator. Okay, so we have A1, which is 3. All right, we're going to divide that by 113 and then multiply it by our force. Okay, so we get 286 newtons. All right, that is our answer to part A. All right, so a pretty manageable force, right? A much smaller force than is needed to lift the car without our apparatus here. Okay? Okay. So now let's take a look at part B. All right. So in part B, we say, how far would you have to push the left piston in order to lift the car? 1 meter. Okay. So we basically want the car to go a distance of 1 meter. Right. So we need to want this to be 1 meter. And we need to know, well, how far do we need to push this little piston? Right. And here, let's kind of put it to use different scale here. I'm going to say this right here is our 1 meter. All right, and so then how far do you have to push this? Well, we'll show that it's actually a very large distance. All right, and so this is what we're looking for. Okay, I'm going to call this D. So why is that? Well, because even though we're getting a mechanical advantage, our force is getting multiplied. Energy can't just be created out of nowhere. We still have to have conservation of energy, which basically tells us that the work in has to equal the work out. So I'm going to say, by conservation of energy, W1 equals W2, which is to say force times distance. So we'd have F1d is going to equal F2d, d1 and d2. All right, and let's add that subscript to the picture. All right, and d2 is given as 1 meter. So then, and we know F1 and F2, so we simply need to solve, and we know that from Pascal's principle. So now we just need to solve for d1. All right, so d1 is going to equal F2 divided by F1 times d2. All right, so that's going to be our 1.08 times 10 to the 4 newtons divided by 286 newtons. All right, and then all multiplied by 1 meter. Okay, so let's take this. All right, divide it by this value here, multiply by 1, but we get 37.7 meters. Whoa, that's a long ways. All right, so obviously you would need a very, very long piston or some sort of catching or ratchet mechanism to actually make this practical, which is often how hydraulics work. All right, so again, this is getting mechanical advantage with a confined incompressible fluid. Thank you.